Hello! Right, okay, so this is the last waves video. It's about stationary waves. So what you need to be able to do by the end of this video is explain the formation of stationary waves, define the terms node, antinode, fundamental frequency and harmonics, determine standing wave patterns from calculation and experiment, and experimentally determine the speed of sound using stationary waves. I might intersperse the word standing waves, just the same thing. So, what is a stationary wave? Well, we need to think about what a progressive wave is first. And a progressive wave is, as we said at the beginning of the video set, it's a wave that transfers energy from point A to point B. A standing wave, or a stationary wave, on the other hand, doesn't. It is formed as a result of the superposition of two waves that interfere with each other, or superpose on each other if they're travelling in opposite directions. And I'll show you a little gif of that will change your life shortly. I made such a bold claim that I had to cough. They don't transmit energy, as I just said. They stand in a fixed position and have nodes, which are points of zero amplitude, and antinodes, which are points of maximum amplitude. So if you imagine, well, I'll show you in a minute actually. Why you don't need to imagine, I'll show you. Right, so imagine I set up a setup like this. Imagine a signal generator attached to a piece of string, a vibrator that's attached to the piece of string as well, and then that string is slung all the way over here and held taut by these weights, and it's like being held in place here. It's got a stop called a movable bridge. And if we pluck this string, or get this vibrator to oscillate this string, the lowest formation thing that could be formed from it is this. The first standing wave. It would be the thing that would happen if I plucked it. So imagine I plucked it, I would get it to oscillate like this, wouldn't I? If I did turn the vibrator off and just plucked it, then it would oscillate back and forth, making this setup. Now this would be the simplest form of vibration. We call it the fundamental mode of vibration. And it would vibrate at a frequency called the fundamental frequency of this system. Right? The system could be changed if I made it tighter, or longer, or shorter, or use a different material. Right? So, yes. Now this is a node here. These points are permanent, no amplitude, flat points, they're nodes. And this bit, which is going to go, this peak point is called the antinode. Now if I turn that vibrator on and increase the vibration, eventually I'll get to the point where it'll do this. It'll be doing that. It's like that thing where you do with the skipping rope, and you can actually get it to do more. It forms a new stationary wave, but this time with nan in it rather than just nan. Node, antinode, node, antinode, node. Now we'll find that should be 2 times the frequency of the fundamental frequency. And you can just ramp this up. You can get 3 times, 4 times, 5 times, 6 times, and we call these resonant frequencies. So each one of these will allow a standing wave to be formed on this setup. And we can put this to the test and it's true. So these are standing waves. They don't really do anything. They can give out energy. For example, if I put my hand over an antinode, it'd whack me. I'd feel it hitting me. Now, if it was made of like razor wire and it was very high amplitude, it could really injure me. Or if it was a microwave, it would make a little hot bit of food there. And yes, that is how microwaves work. I'll go into more detail about that later. So this is the GIF. Imagine the green wave is the wave traveling in one direction, and the blue wave is its reflected version. So if the vibrator sends out a pulse or a wave going in, hits a boundary, then it bounces back. It keeps interfering with the one that's coming in, and the constant source of reflection is interfering as well. Now what that means is there are points where it's going to be constantly out of phase, and these are always at the reflection points or the source points. Now the reason for that is wherever a wave is reflected, it goes through a change of 180 degrees phase. I can explain why that is in lesson a bit easier, so I will do. Just accept it for now. So it's gone through that phase change of 180 degrees, and when it then eventually as they both move on, there are points where it gets in phase, and then later on, as we can see, points where it gets out of phase. So this red line here, this is the resultant standing wave of these two superposing on each other. And this is all you will see, despite the fact that it was formed by these two separate waves that are on the string as well. Proper super weird, but that is the resultant wave. That is how standing wave is formed. Now, you do get asked that question quite a bit, and it is a really nice way of getting a few marks if you just memorize a progressive wave is reflected off a boundary, goes through a 180 degree phase difference and superposes with itself, interfering and causing a standing wave. Like 4 marks, it's nice. So let's think about it. Stationary waves on strings, that's what we're looking at the moment. They still follow the rules of cycles of waves. So if we imagine this, we're going to look at half a cycle of a wave and break it down into its steps. So at time 0, t equals 0, it looks like that. At an eighth of a time period, it looks like that. At a quarter of a time period, it's now flatlining. At 3/8, it's like that. And at half a time period, it's back. It's in the opposite orientation to how it was. Now it will go through that whole cycle the other way round, back up to where it started. Now what's really cool is at any given time, any point on that wave cycle is in phase with all the other things on that wave cycle, which is the opposite of true in a progressive wave. But it's very true on a standing wave, because they're all at the same point in the wave cycle. The wave cycle isn't that shape. The wave cycle is it's moving from each one of these things back to the beginning. Some points to note. Things you know already. Flat bits are called nodes. Constant zero displacement. Distance between nodes is always half a wavelength. Distance between antinodes is always half a wavelength. In the region between successive nodes, all particles moving in phase are moving in phase with different amplitudes, and the oscillations in one loop are in antiphase. So that one and that one are in antiphase. If we obviously it's physics, so we're going to put some equations into it, aren't we? So we need to think of what's a general form to say what the size of a standing wave will be for a given length and for a given frequency. So wavelength 1, the first fundamental wavelength, or the first fundamental mode, we call it, is or the first harmonic. They've got so many names, it's upsetting, and I'm sorry. Is in the first case, it's 2 lengths. Because you can imagine, that's the length, it's only getting half a wavelength on it. The second is getting a full wavelength on it, so the second harmonic is getting 2 half wavelengths on it, so lambda is equal to L. And the third harmonic is getting 3 half wavelengths on it, so in this case, lambda is equal to 2L over 3. It's a bit easier to think about it in terms of length. You've effectively got n lambda over 2 is equal to L in each case, isn't it? So, or 2L over n is equal to lambda. That's the nicest way to think about it. So, in the first case, 2L over 1 is 2L, 2L over 2 is L, 2L over 3 is what you've got, and so on and so forth. Now, stationary waves also form in tubes. That's a really awkward thing to try and get your head around, because we think about them like that, but they also get longitudinal waves forming stationary waves. So imagine a wave is propagating in the air down a tube, it hits that end barrier, and then it starts to come back as a reflected sound. Now that reflected sound, if we've continually got a speaker emitting new sound, that will interfere and there'll be points where it's going to be slapping into each other, creating nodes, and there'll be points where it's on its rarefaction stretch, and this is on its rarefaction stretch, and they're going to add up, and they're going to become antinodes. Now, a really cool apparatus that you can see here is you just chuck a load of flour off other fine powders into a tube like this, and then you set this up, and it bunches up in the nodes, because where it's getting an antinode, it's like blowing the powder out, and so you can use this to actually measure the wavelength of the sound, which is quite cool, isn't it? Pretty cool. It's different rules though, because you want an amplitude at the end. You want an antinode, sorry, at the end of the open pipe. So closed at one end and open at one end. So it's going to be a node at one end and an antinode where it's open. So the first one here, lambda is 4L. You don't have a second one because 2 times that first frequency is on a node. So you're going all the way to the third harmonic now, which is 3/4 of a wave is one length, so 4/3 L is wavelength. And then obviously the fourth one's a node, so we have to go 5 times that original value, and we're getting 5/4 of a lambda is L, so 4/5 of L is lambda. You also have it happen in open-ended pipes where it's just antinode, node, antinode. Now you might think, oh, that's just the string in reverse, and you'd be right to think it is. Right, and these are our sort of conclusions. These are the rules for the string. There is a general rule of being 2 over NL. This is the 4 over 2n minus 1 L, and this one is the same as the first one, isn't it? So 2 over n L. So there you go. There are our general rules for standing waves in strings, closed pipes, and open pipes. You can use this setup. You can use this information to make a little experiment where you can determine the speed of sound using something called a resonance tube. Now that's taking advantage of a closed at one end pipe. Now we can vary the length of a closed at one end pipe by submerging one pipe in another tube of water. So by changing the length of the air column in that water there, we can change the effective length of that pipe, and we can test if it's a resonant frequency. So change the height, bang the tuning fork, and see if you get a loud sound. There you go, boom. Move the tube and it'll go boom. It'll get really loud for a bit, and then as soon as you move it, it'll go quieter again, and eventually at another height it will go loud again. Now following those rules, so it'll be the first, third, fifth harmonics, which is nice. Now the way we can do this is we can set it up so that we're going to test each of these points. Now we'll assume that the first one we come across is the first available harmonic, which is the first harmonic, and we can say that this must be true. We're going to add this plus C term as an end correction in there, just in case we're not accounting for something, but we'll show you in a minute how that's get riddable. Increase the length of the air column, a second resonance position is obtained, you get another ooh, and the air column is now vibrating in its third harmonic. First, it's so awkward, isn't it? First, third, it's the third in my eyes. Some people call it the first harmonic, and then the first one is the fundamental mode. It's annoying. So it'll have 2 nodes and 2 antinodes. That's the second available state. Whether you call it the first harmonic or the third harmonic, who knows? And it follows that rule, 3 lambda over 4 equals L1, plus this correction factor. And then we can do this. 2 minus 1, equation 2 minus equation 1, equals lambda over 2 equals L1 minus L0, and the C's are going to get cancelled out. And then you say lambda equals 2 L1 minus L0, so lambda equals 2 lambda over 2, and we get V equals 2F times L1 minus L0, which is nice. And that's our way of working out the speed of sound. By the way, I realise that what you're supposed to get from that, we will be doing that practical, so don't worry, it will be clear later what we're doing with it. Practice question, do this. have a bash at it. Calculate the wavelength of the stationary wave in a guitar string, and